Abstract data type list. In this video, we will be focusing on three implementations of the interface list: a singly linked implementation, a doubly linked implementation, and one that is said to have a dummy node. That particular list has doubly linked element and is circular. We've already discussed the interface list, so let's review the definition. So you will remember that a list is this linear abstract data type. It's allowing us to store elements. The elements are stored in a linear fashion, meaning that each element has one before and one after, except if you're the first or the last element. Sometimes we say that it's an ordered data structure. We've already seen linear data structures. In particular, we've seen the stack and the queues. So these were data structures that were also linear, except that access to elements was restricted. So the access for the stack was limited to the top, and access to the queue was limited to front and rear. Here there will be no such limitation. In the last lecture, we talked about two implementations. So there was the array-based implementation and the linked implementation. The array implementation, the object of the class ArrayList would have an instance reference pointing at the array that will be used to store the elements of the array list. This array would be created in the constructor. And what is specific about this implementation, the one where we're using an array, is that if an element is added to an intermediate position inside the array, we would be required to shift all the elements from the insertion point to the end, shifting all these elements to the right so that we can insert the element. Likewise, if we're removing an element from the data structure, we have to move all the elements from the point of removal to the end and shift them to the left this time. Because these abstract data types are expected to receive, or we can add as many elements as we want to this data structure, we would also be using the dynamic array technique. In the last lecture, we talked about a linked implementation, so we can review what we've done together. So there is an interface list. It describes the methods that the abstract data type describes. So here we have add first, add last, add, get, remove first, remove last. These are slightly different methods than in the last lecture. They're the ones I want to focus on today. So our linked list implements the interface list. In order to do so, we are using objects from the class node. It's a static nested class. The objects that are stored in the list, they are stored inside objects of the class node, and specifically it's the variable value of the class node that is used to store these values. And each object of the class node, which is acting as a container, is connected to the next one using the instance variable next. In the case of the singly linked implementation that we looked at, the object of the class linked list has an instance variable called head that is used to point at the first element of the list. So the memory representation looks something like this. The objects of the class node are represented here with these circular representations. The bottom part of a circle is the instance variable next. The upper part of the circle is the instance variable value. Here, to the left, we have the object from the class linked list. To be more accurate, as you've seen in our implementation, the object of the class linked list also has an instance variable called size, which is used to record the number of elements that we have presently stored in this list. Okay, so it's the logical size of the data structure, and in the case of the linked list, it's also the physical size. So in the last lecture, we saw that it was useful to store the number of elements. That makes it easier to determine if the index that we're looking for is outside of the range, if we should be throwing an out-of-bound exception, index out-of-bound exception. So, what was complicated or specific about this implementation was that the methods that we want to implement are instance methods that are executed in the context of the object of the class linked list. When we are in the context of the object of the class linked list, our view of the list is through this variable called head. And as the diagram is showing, we only have access to the first element of the list. One of the first things that we wanted to do was to add an element at the end of this list. Of course, there would be a way to accelerate this method, and we will talk about that in a second. But first, we wanted to explore how we would add an element at the end of the list when we have only access to the object designated by head. Okay, so it's clear that if we are to add something at the last position, the element would be to the right of the last one. Here, I pretend that I want to add the value E to this list. It will become our new last element, therefore the instance variable next of that node will be null. Okay, so remember, bottom part next, upper part value. And then in order to add the element, we actually need to change the content of the variable next of the current last element. So we needed a mechanism that would allow us to actually traverse the list, meaning walking from the first node to the last node. And the idea was to use a local variable, which I like to call P for pointer, who would first point at the element designated by head. Okay, so because P is pointing at a node, P is of type node. The initial value of P would be head. And then we needed a mechanism to move P to the next element. Where do we want it to point? We want it to point where P.next is currently pointing. So this means that we will say P equals P.next. Grab the content of P.next, store in the variable P. The result of that, P is now pointing at the next node. And we would repeat this until a certain condition is true. So while some condition is true, P equals P.next. So at each iteration, the content of P.next, which is this reference here, is stored in the variable P. As a result of that, P is moving forward. We will do this operation going into the while loop until P is pointing at a node, who is the last node of this list. What's particular about the last node of the list? This is a node such that its instance variable next has the value null. So here, as long as p.next is not null, meaning it's an internal node of the list, p equals p.next. What is true when we exit the while loop is that p.next is now null. It's this null value here. So we will stop and we will say p.next is equal to, and then we create the new node. We store DLM, and we know that this is our new last node, so therefore the value of next should be null. Okay, so at first we'll simply create the new node, make sure that it points to the current head. When this is done, save the result to the variable head, so the element has been inserted at the start of the linked structure. Adding at the last position, if we focus on the general case first, the else part. So we're using a local variable p. P stands here for pointer. Initially, we're pointing at head. We know that p cannot be null, because if it was the case, then we would have executed the special case. Okay, so if we are in the general case, this is because head was not null. P is now pointing at the same node as head is pointing. And as long as p.next is not null, we go inside the while loop and we make progress. With each iteration, p will be pointing at the next node in the list. When we exit the loop, we know that p.next is null. Therefore, there's no danger in putting a new value in p.next. And the new value that we're putting in is the reference of a newly created node that will store the value of the parameter, and it has no next. Because we added an element, we will be increasing the value of size. Now, when you look at the code, it screams for a special case. It's telling you there is a special case. Because in the general case, what we are doing is we are changing the content of the variable next of an object of the class node. But this is not true when we are inserting the first element of the list, because in that case, what needs to be changed is the instance variable head of the header of the list. Okay, so you see here the need for the special case. So if head equals null, then this list was empty. It will now contain one element. We're creating this element right here, new LM. It has no next because it's the only element of the list. Okay, and likewise, we have all these other methods. There's a method add that will be adding at an intermediate position of the list. We talked about that in the last lecture. This technique that we developed together, the idea of using a local variable of type node, having p designating the first node, the one designated by head, this technique is very general. We're using it here in the method get. Get returns the value stored in the node at position index. So what we have to do is P will initially be pointing at the first node. You remember that with the list, the first index, just like with the array, the first index is 0. So if the call was for get of 0, then we would not go into the for loop. And we would return p.value, which is the same as head.value. And for values where index is larger than 0, then we would go into this loop, and the number of times that we would go into this loop is proportional to the index, the position of interest. Okay, so we would go into the loop. Each time we would be making progress, we would move P to the next node of the list and simply return p.value at the end. Okay, so it's a very general technique. When you're using linked list, you're using this idea all the time when you have to traverse the data structure. We also have a method remove first, remove last, which is a bit more complex. And we have a method size, isNt, and toString. All these methods are using the same idea. With the toString, I will be returning a string representation of the list. I decided that I would start the representation with the open square bracket. Initially, I'm pointing at the head node. And as long as P is not null, I'm going to go into this loop here. I would like to have separators between the nodes, but I don't want to have one the first time I go into the loop. So if the value of P is pointing at head, then I don't go here into this test. What I will do is I will simply extend the value of string by adding p.value at the end. After I've done that, I'm moving forward one position. For the next iteration of this loop, now P is different than head. I've already processed the first element. So I'm going to start adding comma between these nodes. And again, after the if, I'm extracting the value stored in the current node, adding it at the end of the string, moving forward one position. Eventually, when I'm done adding the last element, the last time I will grab p.next. p.next is null, so the value of p will be null. We're done. We have processed all the elements. Exit, add the closing square bracket at the end, and return the string representation. Okay, the last method that I want to show you is the remove last. So remove last in the current implementation is requiring that we would travel all the way to the end of the linked structure. So obviously, if head was null, this is an error. We should not be calling the method remove last unless there's at least one element. So if head equals null, then we throw this exception. Otherwise, here this is a method that will also be returning the value that has been removed. So therefore, saved of type E will be used to temporarily store this value. So here there's a special case. If the list contains a single element, then we will need to change the value of head so that it's null. There was only one element, we're removing it, the value of head will be null. How do we know that there's only one element? It's because head is not null, it's pointing at a node, but the instance variable next of that node is null, so therefore it means there's only one element. In that case, we save the value found in head.value and we set head to null to remove the one element that was present in the list. Otherwise, we have to traverse the list. To traverse, we start with p equals head. We know that there's at least one element. In fact, we know that there's at least two elements. If there was one element, we would have removed it in the special case here. Otherwise, we know that there's at least two elements. General case. Okay, so p equals head. And now the stopping criteria is slightly different. We don't want to stop on the last node, the one where p.next is null, because that would be too late. In order to remove the last element, we need to stop the one before. So what is it? It's a node such that its next element has an instance variable next who's null. So this is clearly the one just before the last element. So until we find it, we're making progress in the list. We are moving forward. When we exit, we know that P is pointing at a node. Its next is not null. Its next is pointing at another node whose instance variable next is null. So there is one node after the current one. We will take the value stored in that node. Okay, so P is not null. It's pointing at a node. This node has an instance variable next. It's pointing at the node that follows. It's in that node that we grab the value and store it in saved. Now we can remove the last element by saying p.next equals null. Okay, so that's our starting point. That is our current implementation. So in this video, what we're interested in is we want to compare the efficiency of array list and linked list. In order to do this, we have to make sure that we have comparable implementations. So both implementations can store an unlimited number of elements. So therefore, array list is using the dynamic array technique. In order to qualify or to say something about the speed of the methods that we are implementing, what we're going to say is that the execution of a method is slow or variable if the number of operation that it needs to complete the operation depends on the number of elements that are currently stored in the list. Okay, so clearly, with the method remove last that we just saw, in the linked implementation, if I'm asking you, how much time does it take? How many operations will be performed? You should tell me, well, it depends. It depends how many elements there are. If there's 5 elements, I will need to travel all the way to the end of the list. Well, not quite the end of the list. I'm going to stop one element before the end of the list and remove the last element. Okay, so the time that it takes for remove last with the linked implementation will be variable, will be slow. On the other hand, if the time that it takes is independent of the number of elements currently stored in the data structure, we will say that the time that it takes is constant or fast. At first, for instance, with the case of the linked implementation, we simply create a node. We already know where next will be pointing. It's pointing at the current head node. And then store the value or the reference of the newly created node into head. It's not important here how many elements there are in the data structure. If there are no element, 1 element, 100 element, a million elements. It's always the same. Create a new node, make sure its next point at the current head, and make head pointing at the newly created node. Okay, so that's our nomenclature. We're going to say that a method can be variable or constant. The implementation that we have for our starting point is this one, the one where we have singly linked element. The object of the class linked list has an instance variable called head. Okay, so I would suggest that you try to predict. Okay, you can pause this video and try to predict for each of the methods that are in the table which one is constant, which one has time that is variable. Okay, so what we're comparing is the array list and the linked list. Let's start with add first. I'm adding an element at the first position and I'm in an array-based implementation. Is it constant or variable? It's variable because we have to create the whole in order to insert this element, so we have to shift all the elements of the array. The time that it takes depends on how many elements are currently stored inside the array. The linked implementation, we already talked about it. We said that it's constant because the time that it takes is independent of the number of elements that are currently inside the linked structure. Add last for an array-based implementation. Is it variable or constant? Again, if necessary, pause the video, try to solve this by yourself. It's variable because when we're adding at the end, the array might be full. We now need to use the dynamic array technique, create a new array, copy all the elements from the old array to the new array, and then make the insertion. Add last. We looked at the method add last together for the linked implementation. We need to traverse the list, therefore the time will be variable. Add for the array-based implementation, it's variable because we have to move all the elements from the insertion point, from pause to the end. We have to move them towards the right, towards the higher index of this array in order to insert the element. For the linked implementation, similarly, the time that it takes is variable because we have to traverse the list all the way to the insertion point. Get for an array-based implementation. So hopefully you remember that in the first lecture of the semester, when we talked about the memory representation, when we talked about the memory, the random access memory, we said that one thing we really like about arrays is that obtaining the content of a cell of an array can be done efficiently. The time that it takes to do a lookup, to consult a position inside an array is constant. And therefore here we're able to implement get in constant time. Get for the list requires traversing, therefore the time is variable. For the array implementation, remove first will be slow. The time that it takes will depend on how many elements there are, because when we remove the first element, we need to move all of the current values towards position 0. They need to be shifted to the left by 1 position. On the other hand, with the linked structure, removing the first element is easy, efficient. This is just like pop for a stack, or this is like the dequeue for the queue-based, for the linked implementation of a queue. Remove last for the array list is tricky. It's tricky because I've not given you enough information to answer that question. So the time that it takes for remove last depends. If this data structure is only growing dynamically and never shrinking, then the time that it takes for remove last is constant, because we would simply remove the last element, put a null value there to avoid memory leaks, and change the value of rear or its equivalent to make it point to the cell before the last position. On the other hand, if this is a data structure where the data structure is shrinking as we are removing element, then remove last would be variable. Finally, remove last for the linked implementation requires us to traverse the list, so therefore the time is variable. Okay, so you see that for some operations, when one implementation was fast, the other one was slow. So you see here that accessing the first position of the linked list is always fast. However, when using an array-based implementation, this is an operation that is slow. When we are reading the content of the intermediate position of the array-based implementation of a list, this is fast. However, for the method get for a linked implementation, this will be slow. Okay, so based on this discussion, it should be clear that the linked implementation is useful when we're accessing the start of the list, and the array-based implementation is useful when we're having a lot of read access to intermediate positions of the list. Okay, so now we would like to accelerate as many methods as we can, and we're going to start by accelerating add last. It should be obvious from our previous discussion on the linked implementation of a queue that the trick here to accelerate add last is to keep a reference to the last node. Okay, so removing elements from the front of the queue was fast because we had a pointer to the first element, and when we wanted to implement the method enqueue in an efficient way, we added an instance variable pointing at the rear element. Okay, so we're going to do the same thing here, and we're going to call this reference to the last element. We're going to call it tail. Okay, so when the list is empty, both head and tail are null. Otherwise, head is pointing at the element at the index 0, and tail is pointing at the last element. And so this technique would make it easy to add an element at the end. We would say tail dot next equals to new node. This is to store a new value, and because this is the last element of the linked structure, its next will be null. Okay, so we're creating a new node to store some value. This is the last node of the list. Its instance variable next is null. The result is stored in tail.next. Now the diagram is making this very explicit. What we now need to do is to move tail forward. So tail equals to tail dot next. And this makes adding an element at the end of this list easy. Okay. So what are the changes to our implementation? So we now have a head and a tail. When we're adding at the first position, perhaps this list was empty. So now when we're saying head equals new node, if tail is null, then we have to make sure that tail is also pointing where head is pointing. We had a list that was empty. We added a new node. Now head and tail are both pointing at the new node. If tail was not null, it means that there were some elements that were already in the data structure, and tail will continue to point at the last element. Now the whole point of adding a tail pointer was to accelerate the method add last. Okay, so we still have this special case. The list is empty. We're going to have that head and tail are both pointing at the new element that has been added to the data structure. However, we no longer need to traverse the data structure in order to add at the end. We said that we can say tail.next equals to new node to store the value of the parameter. And if we want this to work for the next call to the method add last, we have to make sure that tail is now pointing at the new last element. So tail equals tail dot next. Okay, so now we see that add last, its runtime, its execution time is independent of the number of elements there are. It's not true that if there are hundreds, 100,000 or millions of elements that we will have to traverse the list. We now have a direct access to the last element. This is a small change, but it has to be reflected everywhere. If I'm adding at position 0, and if this list was empty, then I need to make sure that tail is now pointing at the new node. With get, there's no structural change to the list, so that should not matter. Remove first. So remove first, if there was no element, it's an error, we throw an exception. If there's at least one element, it's going to work. But if there was only one element, if after removing this element, we have that head is now null, then we have to make sure that tail is also null. Remove last, similar idea. If there was only one element, now head and tail are both null, otherwise proceed. Okay, so we see that the fact that we now have a reference variable to the last element was useful to accelerate add last. However, it makes every method now a little bit more complicated. We have to make sure that tail is adjusted when it needs to be. Okay, so we now have at last fast. The execution time is independent of the number of elements that are in the data structure. Would it be the case that by any chance having a reference to the last element was also making remove last fast? Is it possible? Okay, I'm simply looking here for a diagram. Let's remove what's on the screen. Let's remove these annotations. Okay, so if I want to remove the last element of this list, what I need is I need to change the instance variable next of the node before the last one. I need to make this null, and I need to make sure that tail is now pointing at our new last element. Okay, so this is inspiring me a new possible implementation. In order to add or remove something at the front of the data structure, what's useful is to have an instance variable head pointing at the first element. In order to add at the rear of this list, at the tail of this list, what's useful is to have an instance variable tail. What I'd like to propose is that in order to make remove faster, I'm going to add an instance variable called previous to the header of the list, to the object linked list. Okay, so my intuition is that it's going to be useful for removing the last element. How would this work? So in order to remove, so perhaps I need to save something. So I'm going to say saved is a local variable of type E. Saved equals to tail dot value. Okay, so now saved is pointing here. Now I'm going to cut the link here. So this will be previous dot next equals null. Then I need to make sure that tail is pointing where previous is pointing. So tail equals previous. Okay, so removing the last element is fast. It's easy. All right. It should be obvious that I just painted myself in the corner, because now if there's a new call to remove last, it should be the case that previous should be pointing at the node before, so that we can save what's there, we can cut the link previous.next equals null, and we can move previous backward. But this is giving us a good starting point for our next implementation. If I want to remove the last element of this linked structure, I need to access the element before. Now there could be another call to remove last, and in order to remove our new last element, we would need to have access to the element before. Again, there could be a call to remove last, and in order to remove that element, we would need to change the variable next of the element before. Okay, so that suggests a new implementation, one where the nodes, the objects of the class node, they now have an instance variable next pointing at the element that follows, but they also have a variable called previous that will be pointing at the element before. And this is true for every node. This will be convenient because we can now traverse the list in both directions. If I would like to print the elements in the reverse order, I could say p equals tail. So p would be pointing here. Print the value, and then p equals p dot previous would make p point here. We would display c. P equals p dot previous. Print p dot value. It's b. P equals p dot previous. Print the value. It's a. P equals p dot previous. So p has now value null. So how would we implement this? How would we make the nodes doubly linked? Well, this means that now each object of the class node has a variable called previous. For convenience, we're going to change the constructor as well so that we can initialize the variable previous. So this previous equals previous, like this. If we have this, I'm pretending that remove last will be fast. Okay, so, and we're particularly interested in the general case. So before we needed to traverse the list. Now what we can say is saved equals to tail dot value, tail equals tail dot previous. We're moving backward. Tail dot next equals null. Let's cut the link from tail to the node that used to be the last one. Okay, so now our implementation is simple. Here on the slides, we don't have the precondition checked, but for clarity. But you see, if this list contains a single element, now head and tail are null. Otherwise, general case, move tail to the previous node, make tail.next equals to null. Okay, so if you paid attention, you've seen a slight difference between my coded implementation and the slides. In the coded implementation, I'm using previous, where here I'm using prev. Okay, so now remove last is fast. And you see that accessing the linked implementation at the start or the end is now fast. Okay, so it's a small price to pay to make every node doubly linked. The biggest price to pay is in the complexity of our implementation. Let's look at the method add add will be adding an element at some intermediate position. So first we have to check the prerequisite. If LM is null, we don't like that, throw null pointer exception. If pos is out of range, throw index out of bounds exception. There will be several special cases. Let's start, so here, hence the S here. So obviously, making changes at the start of this list is special because we will need to change the value of head. So adding at position 0 is a special case. Remember that when we're executing this statement, we're first executing the right-hand side. So we take the current value of head and store this inside the instance variable next of the new node. Okay, so B used to be our first element. It was designated by head. This value is now stored in the instance variable next. So the new node that was created is pointing at the old head node. We know that this new node will not have a previous node, so we initialize previous with null. And when we're done, after the call to the constructor terminates, we store the reference of the new node in head. So head is pointing at the new node. If you look at the diagram carefully, and really I truly believe that drawing memory diagrams for linked structure can be very, very useful. So if you look at the diagram very carefully, it's clear that one link is broken. We now need to make sure that our second node is pointing at the new node that was inserted. So I can do this like this. So head is pointing at the first element. The instance variable next brings me to the next node, the second one. I want to change the instance variable previous of that node, and I want it to point where head is pointing. That's the red arrow. Okay, so inserting at position 0, we create a new node. Its next is the current head. And we have to make sure that the second node, its previous variable, points at head. Is it always possible? Well, maybe not. If the list was empty, it's still valid to add at position 0. It will become our new first element. But if the list was empty, then head.next is null. Trying to access previous would generate a null pointer exception. So the special case has a special case. If tail is null, then the new node that was added is the only node. Head and tail are both pointing at it. Otherwise, there was at least one node, and the previous of that node will now be pointing where head is pointing. The general case, so we want to add at some intermediate position. So currently, A is at position 0, B is at position 1, and our current position 2 is holding the value D. the new element that we will be inserting will become our new 2. We would like that the previous will be our current 1. Its next will be what is currently our element at position 2. We need to make sure that the element before is pointing at this new node and the element after its previous is pointing at the new element that has been added. Okay, so we need to traverse the list and we will be stopping at the position before the insertion point. So we stopped at pos -1. When I'm working with a linked list like this, I like to have a variable that will be pointing at the node after the insertion point. So here, P is pointing before the insertion point, and I say Q equals P dot next. So Q is the one that follows P. So now I have a anchor before and an anchor after the insertion point. I can create a new node. It stores the value of the parameter lm. The node before is P and the node after is Q. So here you see this. When the node was created, its instance variable previous is pointing where P is pointing. The instance variable next of the new node is pointing where Q is pointing. When we're done with this, when we return from the call to the constructor, store this inside p.next. So we change the instance variable next of the node designated by P. So it's pointing at the new node. Again, if the diagram has been made and it's clear, you could see that there's a problem or there's a broken link. The node that is designated by Q, its variable previous, is still pointing at the node designated by P because it has never been changed. So now we can fix this. Q.previous will be pointing where P.next is pointing. So here I had a better idea. I used local variables that are called before and after. You're going to see the code looks like English to me. So there is a loop. Before that loop we say before equals head. And now I'm going to go inside this loop, pause -1 time. Each time I'm moving before forward. So before is the node before the insertion point. After the loop, after will be pointing at before.next. What's after? It's the one that follows the node before. When I'm creating the node, its variable previous will be pointing at before, and its variable next will be pointing at the node after. The result of this, the reference of the new node, is stored in the variable next of the variable of the variable before. And then there's one link to be readjusted. So we want to change previous of the node after to make it point at the node that follows the node before. Have we thought of all the cases? Obviously not, otherwise I would not be asking the question. So what if before, when we move all the way in the list until pos -1. What if before was pointing at the last element? If this is the case, then before.next is null. So therefore here we will store the value null inside the variable after. If we are to execute after.previous, again we get this null pointer exception. Okay, so we have to detect this situation. So if before is pointing at the current tail node, then we've extended the list and we added an element after the tail node. So we now need to make tail pointing at the new node that was added. Otherwise, before was pointing at an internal node of the list, and it is safe to change after.previous to make it point to the new node. And here's the complete implementation. So we take care of the preconditions. There's a special case if we're adding at the start. We need to change the value of head. The special case has a special case. Maybe the list was empty. Therefore, there's only one node. Head and tail are pointing at it. Otherwise, the old head node, its variable previous, should be pointing at the new node that was inserted. General case, use a variable called before, find the insertion point, use the variable after to point at the node after the insertion point, create the new node. The node before or previous will be pointing at the node before. The variable next will be pointing at the node after. If it turns out that we're adding at the last position of the list, make sure that tail is pointing at the new node that was inserted. Otherwise, fix the link after.previous equals to before.next. Okay, so as you can see, working with a doubly linked implementation of a list, having a head and a tail pointer is somewhat complicated. So we will now look at another implementation, our last implementation of the list. And this one, its goal is not to accelerate the execution of the methods. The goal here is simply to make the implementation of the list simpler. In what way? In a way that we will be eliminating the special cases. Okay, so that's our next goal, not making the implementation any faster, simply making the code easier to write. So the technique requires something called a dummy node. What's important is that the dummy node will not store any information. It's going to play a very important and special role inside this implementation. Furthermore, the list will be circular. I'll explain in a moment what I mean by a circular list. Here it is. So you have two examples of a doubly linked list with a dummy node and circular. Let's start with the empty list. When the list is empty, its instance variable head is pointing at an object of the class node. And Actually, this is the dummy node. Right now, you see the instance variable size has value 0. It's telling you there's no data. There's no information stored inside this data structure. And yet, head is not null. Head is pointing at an object of the class node. As I said before, the dummy node is not used to store any information. The instance variable value of the dummy node is null. It will always be. It's a circular list, meaning that next is pointing at the dummy node itself in the case where the list is empty, and previous is pointing at the dummy node. Let's look at the general case. Here's a list. It contains 3 elements. This is what size says. Has B, D, F. You see here that, again, the list starts with a special node, an object of the class node called the dummy node. Its instance variable value is null. This node will never store a value. The role of the dummy node is special. I'll explain why in a moment. So here, in the case of a list that contains 3 elements, the value of next of the dummy node is pointing at our first true node, the one that contains B. Its next is pointing at another node. It's the node that has the value D. The next of that node is pointing at the last node of this linked structure. This is where the value F is stored. And as explained, this list is circular. So the value of next of the last element of the linked structure is pointing at the dummy node. And the variable previous of the dummy node is pointing at the last element. This will be very convenient for several reasons, one of which, we don't need a tail pointer. If we want to go to the tail, to the last element, tail is always head dot previous. In a circular list, if we follow head dot previous, the destination is the last node. Okay, so that seems very complicated at first. At first you say, wow, why are we making everything so complicated? Okay, so it takes a few minutes to, and maybe a bit more than a few minutes to absorb this. So here, when you look at this structure, one thing that should be clear is that none of these instance variable of type node, so none of the next, none of previous, is null. So you see, if you look at all of them, all the variable next are not null. Likewise, all the variable previous, none of them is null. So immediately it should be clear that we will never write something of the form while P is not null, or while P dot next is not null, because that will never be true. If you want to traverse this data structure, So we would initialize P to be pointing at head.next. That would be our first element. And we would print P.value. In order to move forward, as always, P equals P.next, we're moving forward in the data structure. We can print P.value. We now want to move forward, P equals P.next. We are now on the last element of the data structure. We print P.value. Now it's dangerous. If we were to continue and say P equals P.next, we would now reach the dummy node, and we can easily be trapped into an infinite loop because every time P.next is never null, we can make progress. So how do we recognize the end of a circular list? The easiest way and the safest way is the last node is a node such that its instance variable next is pointing at the same place as head. So when you have that P.next equals head, P is pointing at the last element of this data structure, of this linked structure. Okay, so I'm trying to find the screen that I wanted to show you. So here I am showing you 3 different lists. There's an empty list, size is 0. There's a list that contains 1 element, size is 1. There's a list that contains 3 elements, size is 3. In all the cases, you see that the number of objects of the class node is 1 more than size. Why? Because all these lists are starting with the dummy node. So, how will this work? Let's say that we want to insert an element at the end of this list. So we need to have before pointing at the last element. As always, I like having a variable after pointing at the node after the insertion point. So here, after is before.next. So after points at the dummy node. With this, I can create a new node. The node before this node is designated by before. The node after is designated by after, so it's the dummy node. We will store some information inside this node, say G. And the result, when the new node has been created, will be stored in before.next. There's only one link that needs to be readjusted. The node after its previous is before.next, and the node has been inserted. Okay, so here, if I want to add at the end of this list, So what we say is before is the last node. What's the last node? The last node, we said it's head dot previous. When we create a new node, the reference of the new node is stored in the variable next of the element before. We're creating a new node. To store some LM. Its previous should be the node before, and its next should be the one after. When we're done inserting the node, we need to change the value of after dot previous or prev, depending on how we decided to implement it, to point at before dot next. And the beauty of this is this would work if there was only one element, if there are three elements, but it also works in the case where the list was empty. So before equals head dot previous, before would be pointing at the dummy node. We're creating the dummy, and then, whoops, we're missing one statement here. I didn't write after equals 2 after equals 2 before dot next. All right, so now after, in the case where it's empty, after is pointing at before dot next, so therefore after is the dummy node. That makes a lot of sense. The list was empty. There's only one node. Before and after are pointing at it. Okay, so before equals head dot previous. After equals before dot next. We create the new node. So the new node is created. Previous will be pointing at where before is pointing, which is the dummy node. Next will be pointing where after is pointing. So after will be pointing at the dummy node. The reference of the newly created node is stored in before dot next. And then after dot previous will be pointing at before dot next. The node has been inserted into the list. And we could do the same for adding information. Or removing information, I should say. To remove some information, we have to position a reference before the element to be removed. We have to position a reference after the element to be removed. And in order to remove, we would say that before dot next equals after, and after dot previous equals before. And the beauty of this is that this works to remove the first element, the last element, any element in between. It works as long as there's one element, and it works for an unlimited number of elements. Let's look at an implementation together. This is the class linked list. Here I decided that the nested static class was called LM. These nodes are doubly linked. Now, if you remember the diagrams, when the list is empty, and in particular it would be empty when we create a new list, there is one node, it's the dummy node. So now the constructor of the class linked list creates the dummy node. The dummy node is circular, so we have to make sure that next is pointing at the node itself and previous is pointing at the node itself. Here, you have to make sure you don't fall into a trap. We cannot write the following. That would not work. Why? Because the equals is executed in two steps. First, the right-hand side. If I'm executing the right-hand side, currently head is null. So I would store null values in previous and next. So that does not work. It's not the correct way to create the dummy node. We have first to create the dummy node and save its reference into the instance variable head. Then we can use the value of head to create the circular list. In this implementation, I had a good idea. I created a helper method. So it's a private method called addAfter. addAfter is provided with the reference of the node just before the insertion point. So after will be pointing at the element that follows the node before. We're creating the new node. Its previous is before. The one after is after. The result of this is stored in before.next. So it becomes the new node that follows the node before. And now we have to change after.previous to make sure that it points at the same place as before.next. Likewise, I'm creating a method removeAfter. It's a private method, it's a helper method. removeAfter is called providing the reference of the element, the node before the removal, the node to be removed. Here, after is the one not immediately after the node before, but the one that follows. Okay, so remember, we want to remove a certain node. Before is pointing at the node before this node. Before.next is the node to be removed. Before.next.next is the one after. In order to remove the node, it's easy. Before.next is equals to after. There's one link that is still wrong. We have to change after.previous to make sure that it points to the node designated by before. Having these two helper methods will make the implementation of all the other methods simple. add first. We're going to be adding after the dummy node. Head points at the dummy node. We call the helper method add after. It does the job. We would like to implement add last. What is the location? How do we talk about the last node? It's the one before the dummy node. Head.previous. We call add after, passing the reference of the last element of the list, the one that's before head. We want to add at some intermediate positions of the list. Let's make sure that value is not null. Let's be sure that pause is valid. After that, before equals head. I'm going to go into this loop. How many times? Pause time. Here, remember, head is the dummy node. I'm positioning before on the dummy node. This is like being on position -1. That explains why I'm stopping at pause. If I was starting on the first real node, I would start on head.next and I would stop at pause -1. So here, to me at least, it's clearer. I start on the dummy node, I go into this loop, pause time. Now pause is positioned, or before is positioned on the node before. I'm calling my helper method add after. Remove first. We want to remove the node that follows the dummy node. So we call remove after, passing the reference of the dummy node. It will remove the first element. We want to remove the last element. Head.previous is the last element of the list, the one to be removed. We're going to pass head.previous.previous to the method remove after so that it removes the last element. Okay, so as you can see, implementing all the methods of this doubly linked structure is now easy. There are no longer special cases. It's even better. We can write two simple auxiliary helper methods, add first, remove first, and call them from the other methods. Okay, so we'll make this implementation available to you. Play with it. Initially, this looks slightly complicated, but once you get the hang of it, it's very trivial to use. Okay, so we've seen that having a reference to the last node was an easy way to accelerate the method add last. We've seen that having a reference to the last element was not enough to accelerate the method remove last. For this, we needed to have doubly linked node. This way, we can start with the tail element, move tail backwards, tail equals tail.previous, and remove the element. It's now also making it easy to traverse the list in both directions. However, having doubly linked nodes with a head and a tail reference means that there were many special cases. In order to simplify the implementation, we could use an implementation where the list always starts with a dummy node. This list is also circular, and when we do this, there are no longer special cases. There are no special cases because every time you want to remove a node, you're changing the instance variable next of the node before and the instance variable previous of the node after. This is true at the beginning, at the intermediate positions, and at the last. Likewise, if you want to add an element, you're going to be changing the variable next of the element before, you're going to change the variable previous of the element after, and this will work if you're adding at the beginning, at any intermediate position, or if you are adding at the end. That explains why we needed the dummy node. This was such that every node has a previous node, every node has a node after. In our next lecture, we're going to take the challenge of accelerating one more operation on the list. We would like to be able to traverse the list in an efficient way. In order to do that, we will have to implement a new concept. We're going to have to create an iterator for the list.